When people first learn Linux software installation, they often assume everything comes from the same place and behaves the same way, like a single universal store with one set of rules. Then they encounter programming language ecosystems, and suddenly software appears to have multiple parallel worlds, each with its own packaging style, version rules, and failure modes. This can feel confusing, especially for beginners, because the system already has a package manager, but now the programming language seems to have its own package manager too. In this episode, we build a clear beginner mental model for why ecosystems like Python Package Index, PyPI, accessed through pip, Rust packages managed through Cargo, and JavaScript packages managed through npm exist, and why they break in different ways. The goal is not to memorize commands or special flags, but to understand the kinds of problems each ecosystem creates, what those problems look like when they surface, and how to choose safer habits when software depends on these ecosystems. Once you understand that each ecosystem is solving a different kind of developer problem, their risks and failures start to feel more predictable. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A language ecosystem is best understood as a community-driven distribution system for libraries and tools written in a particular language. Instead of relying on your Linux distribution to package every possible library version that every developer might want, the language community publishes packages in a way that moves quickly and supports many combinations. That speed is useful for developers, but it also means the ecosystem's priorities can differ from a Linux distribution's priorities. A distribution often aims for stability, consistent updates, and coordinated dependency sets, while a language ecosystem often aims for flexibility and rapid iteration. The result is that you can have two packaging universes on the same machine, one managed by the operating system and another managed inside a language runtime. This matters for security and reliability because each universe tracks dependencies differently, resolves versions differently, and leaves traces on disk differently. When something breaks, the first step is figuring out which universe the software came from, and therefore which rules apply. Cargo is associated with Rust, and its ecosystem has a different philosophy that influences how it fails. Rust places a strong emphasis on reproducible builds and explicit dependency tracking, and Cargo typically records dependency choices in a way that makes builds consistent across machines. This can reduce the chaos of version drift, because the project can lock down exact versions and produce the same results in different environments. However, Cargo's failures often show up earlier in the process, because it tends to enforce rules at build time, and Rust strictness means incompatibilities are often caught before a program even runs. For beginners, that might feel like the system is more picky, but it is actually a trade-off that aims to reduce runtime surprises. Cargo can still run into problems, especially when dependencies rely on native system libraries or when the build environment is missing required components. But the pattern is often a build failure rather than a mysterious runtime crash. When you think about Cargo, think about strong tracking and early validation, which changes the texture of its failure modes. npm is associated with JavaScript and Node.js, and its ecosystem is famous for being extremely large and extremely nested. JavaScript projects, especially web and server-side tooling, often depend on many small packages, and those packages depend on many others, creating deep dependency trees. npm's failure modes often include dependency explosion, version conflicts deep in the tree, and surprising behavior changes when a tiny transitive dependency updates. Even when a project seems small, it can pull in hundreds or thousands of indirect dependencies, which expands both the attack surface and the chance of incompatibility. Beginners often discover this when an application suddenly breaks because a dependency version changed, even though the top-level package they installed appears unchanged. In other cases, problems surface as missing modules, inconsistent behavior between machines, or build toolchain issues that are really about the dependency tree. When you think about npm, think about scale and complexity, because its failures often come from the sheer size and dynamism of its dependency graph. One of the most important beginner ideas is that these ecosystems often manage dependencies at a different granularity than the operating system. A Linux distribution package might bundle a library version that is considered safe and stable for the distribution, but a language ecosystem might want a newer version for a specific feature. That difference leads to tension because both worlds might try to satisfy the same logical need, like a cryptography library or a networking library, but they do so through different packaging mechanisms. Sometimes the language ecosystem uses pure language code, which is easier to distribute and less dependent on the system, but sometimes it uses native extensions or bindings, which tie it back to system libraries. Those native pieces are where failures can become confusing, because the ecosystem package manager may succeed in downloading a package, but the package might not function because the underlying system dependency is missing or incompatible. Beginners often misinterpret this as the language ecosystem being unreliable, but it is more accurate to say it has a different boundary and therefore different assumptions. Understanding that boundary helps you diagnose where the real dependency problem lives. Security risk also looks different across these ecosystems, and that difference is closely tied to how packages are published and how quickly they change. Language ecosystems often allow anyone to publish packages, and while there are community norms and scanning efforts, the barrier to entry is lower than a curated distribution repository. That creates a supply chain reality where malicious packages, typo squatting, and compromised maintainer accounts can become real threats. A beginner-friendly way to understand typo squatting is to imagine someone publishes a package with a name very close to a popular one, hoping you mistype it and install the wrong thing. That kind of risk is more common in fast-moving ecosystems with huge numbers of packages and informal publishing. It is not that Linux distribution repositories never have risk, but the distribution typically has additional curation layers, which changes the probability and the response process. In exam language, you should treat third-party language packages as an expansion of the supply chain and therefore a reason to think carefully about trust and verification. Version resolution is another place where these ecosystems differ, and it strongly influences their failure patterns. In the Python world, version constraints can be flexible, and different projects may select different compatible ranges, which can lead to conflicts when those projects share an environment. In the Rust world, Cargo's model tends to be explicit about dependencies, and projects often carry lock information to encourage consistent builds, which reduces the chance that a dependency silently changes. In the JavaScript world, NPM projects often use lock information as well, but the sheer volume of dependencies and the frequency of updates can still produce surprising outcomes, especially when indirect dependencies shift. Beginners sometimes assume that a version number always means the same thing across ecosystems, but version semantics and compatibility promises vary by community. The safer mental model is to treat version selection as policy, not as a simple numeric comparison. If you are trying to predict how a system will fail, pay attention to how tightly versions are pinned and how many layers of dependencies are involved. Another common failure pattern is environment confusion, where you believe you are running one set of dependencies, but the runtime is actually using another. In Pip's world, this can happen when multiple Python environments exist and your script runs under a different one than you intended. The symptom might be a missing module or a module version that appears wrong, even though you installed the right thing earlier. In NPM's world, environment confusion can show up when global installs and project local installs compete, or when the runtime picks up a different module path than expected. In Cargo's world, environment confusion often shows up as a build using different system libraries than you assumed, particularly when native dependencies are involved. These are not just annoying details, because they create situations where you cannot reproduce behavior reliably, which is a big problem for both security and troubleshooting. A disciplined approach aims for clarity about where dependencies live and which runtime context is executing the code. Conflicts in these ecosystems also differ in how visible they are to the learner. Pip conflicts often feel like runtime errors that appear when code tries to import something, because Python is frequently executed as scripts that rely on runtime resolution. NPM conflicts can appear at install time, build time, or runtime, depending on what the project is doing, and they can be deeply nested, which makes them feel opaque. Cargo conflicts often show up as build time failures, because Rust's compilation process and Cargo's dependency checking tend to surface incompatibilities earlier. Each of these patterns leads to a different troubleshooting mindset. With pip, you learn to suspect the environment and library versions when imports fail or behavior changes. With npm, you learn to suspect the dependency tree and indirect packages when something unrelated seems to break. With Cargo, you learn to suspect build prerequisites and version compatibility when compilation or linking fails. The exam tends to reward learners who can recognize these patterns without needing to be experts in each ecosystem. Rollback thinking applies here too, but it looks different because language ecosystems often install lots of small pieces that are not tracked by the operating system package manager. If you install Python packages into a shared system location, rolling back can be messy because you have to remember what changed and what depends on what. If you install JavaScript packages into a project directory, rollback might be as simple as reverting the project's dependency state, but it can still be complicated if the project relies on global tooling. Cargo projects tend to be more reproducible when lock information is used, but rollback can still be tricky when you mix system-level dependencies with project-level dependencies. The cleanest rollback mindset is to treat each project's dependencies as part of the project, not part of the entire system, and to aim for predictable, repeatable environments. Beginners do not need to become experts in isolation techniques to understand the concept. The more you mix projects into one shared dependency pool, the more likely you are to create conflicts and the harder rollback becomes. Even on an exam, this principle helps you reason about which approach is safer in a scenario. It is also helpful to connect these ecosystems back to repository trust, because language ecosystems are repositories too, just at a different layer. They have their own registries, their own package signing or verification practices, and their own community governance. Some ecosystems support stronger verification mechanisms than others, and the maturity of those mechanisms changes over time, which is why supply chain topics keep showing up in security conversations. A beginner-friendly way to connect this is to treat the operating system repository as one trust boundary and the language ecosystem registry as another trust boundary. Crossing a boundary expands your exposure and your responsibility, even if it also expands your capability. That does not mean you should never use these ecosystems, because modern software depends on them constantly, but it does mean you should understand that you are adding another moving part. When you can explain that clearly, you are already thinking in a security-aware way. By the end of this episode, the main point is that pip, Cargo, and npm are not just different tools. They represent different ecosystem cultures and therefore different failure styles. Pip failures often center on environment mixing and runtime import issues, especially when multiple projects share one dependency space. Cargo failures often surface during builds, with stricter checks that catch incompatibilities early but can confuse beginners who are not used to build time enforcement. npm failures often come from scale, nested dependencies, and rapid change, which can create surprising breakage from indirect updates and complex dependency trees. All three expand your software supply chain beyond the operating system and therefore expand both risk and complexity. If you learn to ask where the software came from, how dependencies are tracked, and what kind of failure a given ecosystem tends to produce, you will be able to reason through exam scenarios and real troubleshooting with much more confidence.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.